Here's another type of resolution, which is the temporal resolution, temporal pertaining to the time. Temporal resolution, as we know, it's related to the time, so temporal pertaining to time. So it is, in definition way, it's the real-time image display against time, temporal, right? So it's strongly related to the frame rate. What is the frame rate? The number of frames per second, or in hertz. So number of frames per second, or number of frames hertz. This is the frame rate. If you look at here, we need to memorize something about the units. For the frequency is in megahertz. For the PRF, pulse repetition frequency, it is in kilohertz, and the frame rate is in hertz. So put this in your mind, that megahertz, kilohertz, and hertz. Okay, the lowest frame rate with flicker-free display to the human eye, I'm talking about the human eye, is around the 16 hertz. So 16 frames per second, the human eye can distinguish them as a continuous display without flickers. Okay, in sonography, usually the frame rate goes in the ultrasound machines is going from 16 to 30. 16 is the lowest flicker-free frame rate, and 30 is the average, or the highest frame rate that can the ultrasound machine can display in average. So to continue with the frame rate we know it is in hertz. It is reciprocal, or it's inversely related in a reciprocal way to the frame time, or the time of the frame. Time of the frame, the units are in seconds. So if I'm having the frame time multiplied by the time of the frame, I get 1. If the frame rate equals 1 over the frame time, and the frame time equals 1 over the frame rate. So these are formulas like any reciprocal. They have 3 formulas, and these are the 3 formulas for the reciprocal of frame rate and frame time. What are the factors that are controlling the temporal resolution, or the frame rate? We have factors and we have limitations, so we need to know the point. Okay, scanning depth is one of the factors and also is a limitation. The sector width, scanline density, and number of focal points per each scanline. So these are the controlling factors. Okay, we have something called the limitation. What is the limitation? We'll discuss this in a moment, which is the propagation speed of sound in the tissues. If you have assumption which is not real but an unrealistic assumption that when we have the propagation speed, it's faster. It's not only 1540 meters per second. Let's say it's like 2000 or 3000 meters per second. What happens? Okay, I'll get the sound beam goes to the target and reflect back very fast, and I will get the frame rate will be much higher because each frame will take very shorter time. So, but this is not the case. That's why usually they call the sound beam propagation speed on the tissues, or speed of sound in tissues, is a limitation to the frame rate. So we need to know this. All right. So, and also we have something that is well known, that the slowest component of the system determines the temporal resolution. For example, if I'm having, for example, the scan converter is lower in processing the defective or whatever, the frame rate will decrease. If I'm having the receiver, it goes slower, so I will get decreased frame rate. So the total frame rate follows the speed, or the how fast is each component in the ultrasound machine. So this is here a chart that discusses the factors that are affecting the frame rate and what will happen of these factors to bring me a better temporal resolution with increased frame rate and a lower temporal time of the frame, and what will happen to bring me a worse temporal resolution with a decreased frame rate and increased time of the frame. So each one of these will be discussed separately. So we have here the scanning depth. For scanning depth, if I'm having a shallow scanning depth like here, what will happen? The frame will finish early, so decrease time of the frame. What will happen next? I'll get higher frame rate. I'll get better temporal resolution. What if I'm scanning deeper, like here? Scanning deeper, what happened? The time of the frame will get longer because it takes longer time to go all the way down to the maximum scanning depth and return back. So the PRP will increase, and multiply this by that. How many scan lines here? I will get the time of the frame will get longer, right? So deeper scanning, I will get longer time of the frame, I will get lower frame rate, and I will get worse temporal resolution. What happened with the sector width? Again, if I'm having a narrower sector width, I'll get improving of the temporal resolution. If I'm getting wider sector depth, sector width, I will get a worse temporal resolution. Scan line density, if I'm having more dense less dense scan lines, like here, less density, what will happen? The frame will finish early, and that's why I will get better temporal resolution. What if I'm having more scan line density? More dense like here, I will get what? I will get worse temporal resolution. The frame rate will decrease gradually. Okay. Again here, number of focal points. If I'm having a single point like here, single focal point like this, the frame will finish early with only one focal point. So there is one pulse per each scan line. This is the basic thing, the very primitive scan line density that has only one focal point. So what if I'm applying multiple focal points? For example, here I'm having 3 focal points. What happened here? Each scan line will receive 3 pulses to finish the scan line. So the time of the frame now is multiplied by 3, or 3 times longer. So, and this will decrease the frame rate. As you see here, I put some red asterisks. Why? Because these are discussing the lateral resolution in comparison to the temporal resolution. So I'm having here some issue in this point, the scanline density and the number of focal points with the lateral resolution. So let me see this, how it works. Okay, although increasing the scanline density or using multiple focal points will lower the frame rate, and as we see this happens, right? But and degrading the temporal resolution, but they improve the lateral resolution. And again, if you remember, we're discussing the lateral resolution here before. Okay, we have lateral resolution is better with multiple focal points, more narrowing of the beam, and also more scan line density. And this will improve the the lateral resolution. But of course, they will degrade the lateral resolution. Okay. Also remember 2 more things. Okay, that the color Doppler and power Doppler, they have the worst temporal resolution, especially the power Doppler. Power Doppler is the worst temporal resolution of all the applications, right? So power Doppler and color Doppler, they have lower frame rate, right? And also we need to know something about the M mode. M mode had the best temporal resolution. But why? Because it's only one scan line. It's not multiple scan lines. It's not an image. It's one scan line as keep pulsating through this scan line, and that's why it's best temporal resolution. Okay, when we might need high temporal resolution, when we might need a high lateral resolution, or why am I require a high temporal? Why am I require high lateral resolution? So high temporal resolution, we need it where? Which if I'm having, which is the high frame rate, okay? If I'm having, for example, an echocardiography, and I need this to capture all the changing events of the cardiac cycle. We know that the cardiac cycle is, the heart rate usually is almost 70 beats per minute, which is a little bit close to the 60. So in 1 second, roughly 1 second or less than 1 second, I have all the cardiac cycle is fulfilled in 1 second. The systole and the diastole, all the valvular closure and openings, all the muscle contraction and relaxation, all this happen in less than 1 second. if I want to get good representation of the cardiac cycle, I need to have higher frame rate. And the frame rate here, if I'm having a high frame rate, I will get better capture of all these events. And in 1 second, I get all these events to happen. I need to capture them and document them. That's why in echocardiography, the machine is automatically referred to the less scan line density, narrower sector size, less power point, less focal point. So these settings are chosen automatically by the default choice of echocardiography. Also, if I'm having flickers, which is not pleasant to the eye, I might choose to increase the frame rate a little bit to make the flicker-free display. Why I might need to improve the lateral resolution on the expense of the frame rate? Okay, why might happen if I'm requiring this in the mostly non-moving organs, for example, the liver, gallbladder, spleen, urebladder, kidney, all these, pancreas, all these, they are not fast-moving objects. That's why I might improve or look for settings to improve the lateral resolution on the expense of the frame rate. Again, as I mentioned earlier, what is the prop speed effect? Prop speed is a limitation, propagation speed is a limitation of the frame rate. Unfortunately, the speed of sound is determined by the medium only, okay? And that's why it's not adjustable, and that's why we cannot adjust the prop speed. And this is why the reason what we call this a limitation. There's something called parallel processing, and I think I need to explain this a little bit. The parallel processing is what? We know that in the regular scanning, that the scan plane is made of like steering of one scan line. One scan line is moving from one right to the left or left to the right, moving back and forth, and this will make the frame. So each frame is made of several scan lines that they are going in succession from one side to side. But what if this will degrade because the frame waits for one scan line to finish all this going back from right to left, but or side to side. But what if I'm able, just in case, I'm able, for example, to operate scan line number 1 and scan number 50. Okay, so by the end of 100 scan lines, I can get the time of the frame cut in half because I get the image now processed together, one half and the other half all are processed simultaneously, and that's what we call parallel processing. So we need to know what's parallel processing. Okay, parallel processing is what? When we get the scan line per processing, when you have the scan line is processing multiple scan lines at the same time. For example, if this is the image here, okay, I can, if the machine can process me the first number scan line here and scan line, for example, number 50. What happens here? I get then number 2 and number 51, or for example, number 1 and number 51. So number 1 will be processed together with number 51, and then 52 will be processed together with 50. Number 3 will be processed with 53, and so forth. At the end, when I get the scan lines here filling all this half, the other half is filled in the same time. So that's why I get what you call parallel processing, which will cut the time of the frame into half, or 1/3 at least in some cases. So in this way, parallel processing is improving greatly the frame rate. Thank you, and see you in other resolutions.